So I wanted to just do a short video with a frame example. I know we didn't talk too much about frames in class, but I still wanted to introduce it with a video. So what I was saying in class is a frame is different from a truss because the members that make up the frame aren't necessarily two-force members. You actually will have some members that are what we would call multi-force members. There's a number of ways that this can happen. One example would be if in the middle of a member, another member was attached. And that would be different than a truss because in the truss, at every joint, it was sort of the joining of two separate members. But this would be if you had a long member and then you just kind of braced it with another member, but it got attached in the middle. The one member that had the other one attached to it can't be a two-force member anymore because the support is exerting a force, that is somewhat at least perpendicular to the member that it's attached to. And so now the forces in that member can't be along its line anymore, but there's ones at angles to it. Another way that that can happen, and this is the example we see here, is a load is not placed at a joint, but it's placed in the middle of a member. And so this is a frame simply because of the fact that I have a 2,000 Newton load in the middle of member BC. And that makes it a frame. Now, when we do frames, it can kind of get messy because what we do is we take them apart and we look at each member individually. But the idea is that if we put them back together, some of the forces that we had diagrammed would disappear in the overall picture because of the way we drew them. And I'm going to show you what I mean in a minute. So we have this frame. We're asked for a specific question. We're going to find the forces at point C that pin exerts on member BC. We're also told to notice that member AB is still a two-force member. That's this piece right here. That actually makes things a little simpler because I can assume that the force that's exerted at this end of BC is going to be along this line instead of writing it in X and Y components. All right, so when we want to solve a problem like this, like I said, we take apart. Okay, I can't use that pen because that's squeaky and that's annoying. We take apart the individual members and we label the forces acting on them. And so, for instance, I wrote, this is member BC. I have force CY and CX. That's a force acting on it. I have the 2,000 Newton force acting there. And then I'm going to draw FAB, which is going to be at a 60-degree angle. Okay? Now, and that's literally what I do. I have looked at this member individually, and I'm going to look at those forces. Now, just to show you what I mean about how the forces would cancel out, if I drew member AB, I would draw the forces acting at the end of it. They would be turned opposite of how they were here. And the idea being that this would be the force on AB at the top. And if I take this member and I put it back together, notice these two forces are going to cancel out. So when I take the frame apart and I look at each member, this is like an external force, but when I put the pieces together to make my frame, these two forces become internal to the system and they disappear because they're drawn equal and opposite. And so that's one of the things that you have to remember when you're working with a frame or a machine is if you put it back together when you're looking at the individual pieces, those forces that aren't external should disappear. All right, so we've been asked to figure out what the forces are at that pin at point C. So I purposely drew my CX to the right. You know, if this is in the right direction, CX isn't in the right direction, but I'm not going to worry about it. So when I look at forces in the X direction, I have the X component of FAB and then CX. They're both on my picture positive, and so I'm making them both positive. If I look at the forces in the Y direction, I have FAB sine of 60 degrees, and then I have minus 2,000 for the load, and then plus CY. And that adds up to be 0. Now I'm going to do the moments about point C in order to actually be able to give myself a third equation. And I chose point C. I know I was trying to find those values, but choosing point C as my point of rotation will allow me to solve for FAB, which you can see is going to let us determine what the X and Y components are at C. Now, when I look at the forces on this member, the Y component of FAB will produce a moment about C. The X component will go right through that point, so that doesn't contribute. And if I'm pointing up as FAB is, it'll cause a clockwise rotation. And so that's why I made that negative. The load will produce a counterclockwise rotation, which makes that moment positive. And so FAB can be found by rearranging this. And I find that it's 1155, and that's newtons. I can then go into this expression, use this to find CX. CX is going to be minus FAB cosine 60, and that will end up to be minus 577 newtons. And so the reason that that was negative is because it actually is a force to the left, and so that's what that negative sign means. CY is going to be equal to 2,000 minus FAB times the sine of 60, and that turns out to be 1,000. And that one turned out to be positive, so my direction was correct, and it is actually in the positive direction. So this is just a really, really simple example of how you would approach a frame, and it really doesn't change even if it's more complicated. It might be necessary for you to look at more than one piece to find what you're being asked to find. And just remember that when you're drawing the forces on the individual members, if you put them back together again, you want to make sure that when you're done, you would only see external forces on your completed diagram. And again, like I was saying, these two forces would cancel out, and so we wouldn't see them in the diagram when it looked like this. All right, we'll talk more about that in class, and I'll do some more examples.